A queue is an abstract data type where elements are inserted from one side, known as the rear or back, and are removed from the opposite side, called the front. It operates on the first in, first out principle. You can think of it like a queue at a market checkout. The person who arrives first will be served first. Queues can be implemented using both linked lists and arrays. First, let's look at the linked list implementation. A solid understanding of linked lists is necessary to grasp this concept fully. If you're not familiar with linked lists, we have a detailed video on the topic available on our channel. You can find the link in the description. In a linked list implementation of a queue, inserting elements at the back of the queue, known as in queue, involves adding to the end of the list. This operation is performed in constant time. Conversely, removing elements from the front of the queue, known as dequeue, involves deleting from the head node of the list, which is also a constant time operation. Let's see the code for implementing a queue using a linked list. First, we define the queue class. In the constructor, we initialize the queue using the linked list class that we covered in our linked list video. Next is the unqueue operation, which involves inserting elements at the end of the list in constant time. The dequeue operation first checks if the list is empty. If it is, the method will print a message and return none. If the list is not empty, it will remove and return the element at the head of the list. This is also a constant time operation. Finally, the peek operation is similar to dequeue, but instead of removing the front element, it returns the front element without removing it from the list. When we create an object using the queue class, it initializes a linked list with no elements, as shown below. The abstract representation of the queue is shown above. It will then perform operations accordingly. Next, let's look at the implementation using arrays. First, we'll consider the naive approach. In this case, unqueuing means appending elements to the end of the array, which is a constant time operation. However, dequeuing involves removing the element from the first position. This operation is a linear time process due to the need to shift all subsequent elements to fill the gap. Can we do better? To make the dequeue operation more efficient, we can initialize a front pointer at the 0th index. Unqueuing will remain the same as before, where we append elements to the end of the array. However, when performing the dequeue, instead of shifting all the elements, we can simply set the element at the front pointer to none and move the front pointer one index to the right. This way, the dequeue operation can be performed in constant time. But there's a problem. Although the dequeue operation now takes constant time, the issue arises when the array becomes filled. The memory space to the left of the front pointer is wasted, as those slots are no longer usable for new elements. To fix that issue, the circular queue comes to the rescue. In this implementation, we initialize two pointers, front and back. Initially, neither pointer is set to any index in the array. When unqueuing the first element, both pointers move to the 0th index. For subsequent unqueuing operations, the front pointer remains in place, while the back pointer moves to the next index as new elements are appended. When dequeuing, the element at the front index is assigned to none, and the front pointer moves one step to the right. Setting the element to none is optional since it will be updated later, but it's generally considered good practice to avoid confusion. The real benefit of a circular queue becomes apparent when the back pointer reaches the end of the array. When this happens, instead of stopping or wasting space, the back pointer wraps around to the beginning of the array and continues unqueuing elements in the available space. And when the back pointer reaches the position just before the front pointer, that's when the queue is considered full. At this point, there is no more room to insert new elements because the next position for the back pointer would overwrite the element at the front. In the coding part, we'll begin by defining the circular queue class. Inside the constructor of this class, we will first take the size of the queue as an input parameter. This size will determine the capacity of our queue and how many elements it can hold at most. Next, we'll initialize the members of the class. First, we'll store the size of the queue as a class attribute. Then, we'll create an array of the same size, initially filled with none to represent an empty queue. Finally, we'll initialize the front and back pointers. Both of these pointers will be set to -1 initially. This indicates that the queue is empty, as no elements have been enqueued yet. Next, we'll create a function that returns true if the array is full and false if it is not. To visualize this, imagine a queue with a size of 6. If the back pointer is at index 1 and the front pointer is at index 2, the queue is considered full. Using these values in the formula will return true. Conversely, if the back pointer is at index 0, the same formula will return false, indicating that the queue is not full. Next, we'll implement a function to check if the queue is empty. This function will simply check if the front pointer is -1. If the front pointer is -1, it means the queue is empty. Otherwise, the queue is not empty. After implementing this function, we'll define all the other methods required for the circular queue operations. The onQueue method takes a value as an input parameter. It first checks if the queue is full using the previously defined function. If the queue is full, it will print a message and return. Next, the method checks if the queue is empty. If it is, it assigns the front pointer to the 0th index. It then moves the back pointer to the index determined by the formula we discussed earlier, which gives the current position for the back pointer. Finally, the method assigns the value to the desired index in the array. The dequeue method similarly checks if the queue is empty. If it is, it prints a message and returns none. Otherwise, it creates a variable to store the value at the front index. It then updates the value at the front index to none, which is optional but generally considered good practice. Next, it checks if both pointers are equal, meaning they are both at the 0th index. If they are, it initializes both pointers to -1. If not, the front pointer is updated according to the formula we discussed earlier. Finally, the method returns the value that was stored in the variable. The display method first checks if the queue is empty. If it is, it prints a message and returns. If not, it checks if the back pointer has a higher or equal value compared to the front pointer. If it does, it returns all the elements from the front to the back in the same order. If the back pointer is lower, it retrieves elements from the front pointer to the end of the array, then takes elements from the beginning of the array to the back pointer and concatenates them. Although there are no visible loops in this code, this operation has linear time complexity because slicing the arrays takes linear time at a low level. Creating an object with that circular queue class will initialize an array along with the pointers as shown below, and the abstract representation of the queue is, as usual, above. The operations will go like this. A circular queue can also be implemented using a dynamic array instead of a static one. In this case, if the queue becomes full, a new array will be initialized, typically twice the size of the original. All the elements will then be copied from the old array in a specific order, first from the front to the end, and then from the beginning to the back element. The front pointer will be assigned to the beginning, and the back pointer will be assigned to the last element. The old array will then be removed, and this new array will become the queue. The code for the dynamic array implementation is similar to the previous one, with a key addition in the constructor, a count attribute that keeps track of the number of elements in the queue. The new function, called resize, handles resizing the array when the queue becomes full. It starts by defining the resize method, where a new array is initialized with twice the size of the original. The method then loops over the elements, copying them from the old array to the new one in the correct order. After that, it updates the parameters accordingly. When performing the onQueue operation, the algorithm first checks if the array is full. If it is, the array is resized before proceeding. Once the resizing is complete, the onQueue logic is executed as before, adding the new element to the queue. Now that was a simple queue. Another type of queue is a doubly-ended queue, where elements can be inserted from either the front or the back. And they can also be removed from either the front or the back. The simplest way to implement a doubly-ended queue is by using a doubly linked list. Enqueuing from the front side of the queue means inserting an element at the head of the linked list, while enqueuing from the back side involves inserting the element at the end of the list. Both operations are performed in constant time. Dequeuing from the front means deleting the element from the beginning of the list, and dequeuing from the back involves deleting the element at the tail node of the list. Both of these operations are also performed in constant time when using a doubly linked list. Another way to implement a doubly-ended queue is by using an array in a circular manner. Enqueuing at the rear works the same way as before. However, enqueuing at the front means adding the element at the position just before the front pointer, taking into account the circular nature of the array, where the position wraps around if necessary. Dequeuing from either the back or the front involves moving one index before, also considering the circular nature of the array. All these operations take constant time. Think of the array like a circle, where the last index is connected back to the first index. First, adding at the back means adding at the 0th index and moving both front and back pointer to that index. Then adding at the back of the queue means inserting at the back and moving the back pointer forward. Enqueuing at the front is like moving in the opposite direction. You add an element just before the current front pointer, accounting for wrapping around if needed. Dequeuing from either end involves moving one step backward in the respective direction. From the front, you move forward one step to remove an element, and from the back, you move backward one step to remove an element. Note that the underlying memory structure is not circular at all. This analogy is just to explain the concept. The next type of queue is a priority queue, which is interesting because it operates on priority rather than just timing. Elements are inserted into the queue and arranged in a specific order based on their priority. When dequeuing, the element with the highest priority is removed first. Think of it like a hospital queue. A person with a sudden heart attack has a higher priority than someone with a mild fever. The implementation of a priority queue is complex and deserves its own video. We'll explore it further when we discuss the heap data structure.